Plenty. Okay, cool. Before we begin talking about evolutionary algorithms, welcome and thank you for having me over. Utrecht Jug and Volkel, of course. Just want to give a quick side note that I only slept for 2 hours tonight because, fortunately, my little boy fell off a slide yesterday and I had to spend the night in the hospital. So that was a lot of fun. But I'm here and he's fine, he's sleeping at home.
You're not.
I guess somebody brought my beer, so we're going to have a good night. So if I'm a bit drowsy because I only slept 2 hours, sorry about that. Evolutionary algorithms. This is a slightly odd question to ask at the beginning of a presentation, but who already saw this presentation? Because as they say, I'm a bit of a conference board, how do you say that? Something I stole from somebody else, the term at least. No, I love talking about evolutionary algorithms, and I always say this is the last time I'm going to give this talk, which was actually the case when I gave it 2 weeks ago at the DevMotion meetup. Told all my colleagues this is the last freaking time I'm going to give this presentation, and then Theodorus messaged me the same evening asking, hey boss, nice presentation, could you come give it over at the Utrecht Jug? I'm like, one more time. But I'm really passionate about the subject. I really like what it does, what it can do for you. It's just nice to talk about and share, because I think artificial intelligence is a bit underrated still in the job world. It has seen a great incline. People at Bol should know about that a little bit.
Here.
Nice. So the term data scientist was unfortunately coined after I graduated and started doing Java consultancy, but we'll get there get to that in a bit. Anybody already hear about evolutionary algorithms? The rest, any clue, or it's just like open mind, beer? Okay. Just trying to check it out. So nature has always been a great inspiration to software engineers like us. And I can already name 2 great examples. One of which being the brain, which created Java and created programming languages, founded Rome, founded Bol.com and the Java Jug, the Utrecht Jug. So this is a great thing, which we base neural networks, for example, upon. And there's also this other thing called evolution, which makes sure this little guy could hide in its surroundings, and which in turn also created the brain. Right? Evolution is a really powerful concept. And there are a few concepts behind it, a few mechanisms behind the concept that we can actually use as programmers and as developers. And that's what today's talk is about. But before we get to that, let me introduce myself. I'm Bas Knopper. I'm Dutch. I've had the privilege and the honor to speak at several conferences because I like talking about the subject. I'm an AI enthusiast. I have a background in AI with a soft spot for evolutionary algorithms. I'm a Java developer, and since recently, starting this year, managing partner of JCore. I'm going to do a bit of shameless promotion. Bear with me, it's only one slide. We're a group of young Java professionals. He's going to turn off the recording. A group of young Java professionals who like to help clients with complex, challenging projects, with the extra reason for the professionals being that we have a lot of knowledge and feeling for the art of development from JDriven, which is the big brother of JCore, and we use that to train and enthuse the people that come work for JCore. These are 2 of the first buddies that joined. So it's pretty great. If you know somebody that's like to start a career, want to be really great developers, let me give you a call. Yeah? So that was that. Now we're going to head back to the interesting part. So what would I like to accomplish today? I would like to gain your interest for the subject of evolutionary algorithms. I would like you to get a basic understanding of the subject. I would like to show you how to use them and when to use them. And ultimately, I would like to add them to your already magnificent toolbox because as developers we use a lot of tools, Gatling being one of them now. And how awesome would it be that in a couple of years you face a problem and you think, hey, there was this crazy guy at the Utrecht Jug that talked about evolutionary algorithms. Maybe we can use that. So I just want to add it to your toolbox. And I would like to have evolutionary algorithms get the attention they deserve, because as I stated before, I think it's underrated. So if you're on Twitter like me, because it's 2016, maybe give a shout out if you like what you see. So what's the agenda for today? We already did an introduction. I'm going to show you how NASA did it, because then it's cool, right? I'm going to show you some evolution concepts just to make sure we're all on the same page. And then we're actually going to go to some puzzle solving time with the Salesman Problem, which we're going to solve today with plain Java code using evolutionary algorithm design. And we're going to have a demo of it as well to show you that it actually works. I'm going to show you some frameworks because I did a demo for you in plain Java to show you how easy it is and how it works. But there are also frameworks, of course, which can jumpstart your use of evolutionary algorithms. And we're going to end with a checklist because it's not always a good idea to use evolutionary algorithms. So what did NASA do this time? There was a Space Technology 5 mission, launched March 22nd, 2006, completed 2006. So that's a while ago. But the interesting part is that they had 3 spacecraft that were like this size. And so they were doing some measurements of the atmosphere. Not very important for this story, still fun though. But what they also needed was antennas on top of those really small spacecraft that were small enough to fit on the spacecraft, but also had to function according to the spec. And that was a bit difficult. I'm already talking ahead here, doesn't matter. That was a need for a solution that was not easy to engineer. Even the NASA guys couldn't come up with a shape and a material for the antenna to make it work in such a small size. So they used an evolutionary algorithm that made these. I wouldn't draw these. It's like mind blown, right? So since NASA can explain it way better than I, and the reason we moved to this room is because we needed some sound, we're going to watch a little movie from NASA. That just shows you, gives you like the American feeling of yay, evolutionary algorithms.
Evolutionary antenna synthesis. Designing and optimizing antennas by hand are time and labor intensive, are costly, complexity is massive, and require significant expertise and experience. The Evolving Systems Group at NASA Ames Research Center tackled a challenging antenna design problem for NASA's Space Technology 5
So
mission.
that's a little antenna right there. That's really small.
They've come up with a computer program that searches for superior designs by repeatedly taking the best antenna designs and using them as parents to breed new ones. Network computers running advanced evolutionary algorithms, generating hundreds of thousands of antenna designs. The survivors go on to produce ever higher performing populations, leaving but a few superior designs. Evolutionary antenna synthesis has the potential to design better and less costly antennas faster than before. The evolved antenna is currently undergoing tests that will tell if it is qualified to launch with 3 satellites on the Space Technology 5 mission in 2004. If successful, this evolved antenna will be the first evolved object to fly in space.
So it's a bit old movie, but it's pretty great what they did there, because at the end she said, it's undergoing tests to see if it's going to actually fly in space, and it did. So I think it's a powerful example of evolutionary algorithms and what it can do. It is actually the first evolved object to travel through space.
That we know of.
That we know of. And that's actually, you're actually the first one to say that. That's cool. Apart from us as well, obviously. But how did they do it? Before we head into that, I just want to take a little step back to talk about evolution again, just so we're on the same page. I'd like to imagine this is how it happened. So if we think about evolution, we probably all think about survival of the fittest. But what does it mean? Well, it means if you have a finite amount of resources in a certain environment, and you have life forms with a basic instinct towards reproduction, that's a really nice way of putting it, you get more and more life forms, and you still have a finite amount of resources. So some are going to make it, some are going to compete better for those resources than others will. So what you get is the ones that are better suited tend to survive, and the ones that tend to survive tend to reproduce. And in that way, the best traits go to the next generations and generations and generations. So, if we were to draw these, and look at these expertly drawn individuals over here, these are depicting, through form and through color, different individuals in a thought of population, in a certain environment. So you can imagine some of these not competing well enough to survive, and unfortunately they don't make it. Others do, and they reproduce. So, recombination. There's also something special that can happen during recombination. Anyone, any idea?
Mutation?
Mutation, thank you. So, mutation. So what happens during mutation? What doesn't happen? Something goes wrong. Simply put, something goes wrong during recombination, making it end up with different DNA than it was supposed to be when they started recombining, if you could put it like that. And what does that mean? Well, it can mean absolutely nothing, because the DNA change doesn't mean anything for the individual. It can be disastrous because it can make the individual that's being born not viable, so it doesn't survive at all.
Yeah.
But it can also mean that a certain trait pops up in the population that is really great. So you might imagine the long-necked horses to grab the leaves from higher trees and higher trees and higher trees and higher trees. And poof, now we have a giraffe, right? It takes a long time, but that's how evolution works. So the next generation, because of these two not making it and these two being introduced into the population, is going to look like this. Now we have a new population that is going to compete for resources and going to reproduce again, and now we get new generations, new generations, new generations, where the best traits tend to survive. Okay, well, that's all nice, but how do we get from evolution to problem solving? Because that's why we're all here, that's why we go to work, because we're going to solve problems. Well, if you have the image of the previous slide, and we said this was the environment, we can also see that as a problem that we're trying to solve. And the individual can be seen as being a candidate solution to our problem. And some solve it better than others. And the funny thing about evolution is that if you go on long enough, you get a solution that is good enough for your needs. That's actually what you're looking for in evolutionary algorithm design. So that was the theory, just a little bit of theory, just to make sure we're on the same page. Now it's puzzle solving time. We're going to do a literally more down-to-earth example than a NASA example. The traveling salesman problem. Who has heard about the traveling salesman problem? Quite a few. I'm still going to explain it, don't worry. So the problem is, given n cities, where n is the number of cities you want to visit, find the optimal route for visiting all cities. So starting in wherever, you have to visit all cities and get back at home for supper. How many of you are playing Pokemon Go? Be honest. There. Are you sure, guys?
No.
Okay. So people that are playing Pokemon Go want to go to Pokestops, want to go to gyms, and want to be home for supper, are actually solving the traveling salesman problem. So they could use Evolutionary Algorithms for that. And the trick is you have to visit every city only once, or you can visit every city only once, and you have to return to the origin city. So the origin city is actually visited twice because you leave there and you get back. So this seems like an easy problem, but the search space is huge. For 30 cities, there are 30 factorial, that's 10 to the power 32 possible routes. Extra beer for the one who knows how to pronounce this number, but that's this amount of possible routes only for 30 cities. So brute force might not be the best solution. Evolutionary algorithms is also not the best solution, but it's going to show you how powerful it can be regarding this problem. And the problem is easy to explain, so it's a great use case to show you evolutionary algorithm design. So plain Java code, which is also always great, especially at the jug. And show you a demo that actually works and not selling air. So what does an evolutionary algorithm look like? So first, we initialize we need to have a population. So we initialize a population with random candidate solutions. So what are candidate solutions? Is the first question you might ask.
Possible routes.
The possible routes, indeed. And one possible route would be a candidate solution. So if we have n equals 6, so we have 6 cities we visit, we label cities 1 through 6, and we have base city 1, then a candidate solution signifying the route would be, for example, 1, 2, 4, 3, 6, 5, 1. But it could also be 1, 4, 2, 3, 6, 5, 1. So these are permutations of the route. And this is a candidate solution. And we can represent this in an array list, in an array, in whatever, comma separated list. This is a candidate solution for us. And why is it so important? Because now we are enabled to calculate distance and talk about it because we have a representation. We can talk about mutation. We can talk about recombination. And we will. But first, we need to evaluate each candidate. You have to have a way of saying this individual is better suited to the problem than this individual. So you have to be able to compare. So how do we evaluate this? It's also called the fitness function. Well, it's the sum distance. That's what we want to know. And in this case, it will be D1 distance between 1 and 2, 2 and 4, 4 and 3, 3 and 6, 6 and 5, 5 and 1, and that's summed up. That's the distance the whole route is going to take. And suppose you go to all capitals in Europe, and you first go through the north and to the south and to the north and to the south, is less performant than like making a circular motion, because you're making a lot of distance going up and down. And what we want to do with this is we want to minimize. We want to minimize this distance. So that's our fitness function. And we're already going to see some code. Yay! So we just want to implement this calculate fitness. It's going to fit on one slide because it's fairly easy. This is probably a pattern we've all seen before. Total distance of 0, we initialize, we're going to calculate the total distance, and we're going to assign it to the fitness of the candidate that we're currently in. So how do we calculate? We're going to visit all cities in the route, and we're going to see what the distance is compared to the next city. So we get the city, we get the next city, and we calculate the total distance by calculating the distance between them and adding it to the total distance. So the more perceptive among you might have seen that this goes to -1, and you might think that's an off by 1. But the last one doesn't have a next, so we need to go all the way to the -1 and up to the end. This is pretty clear, right? I think. If you have questions, please interrupt me. We'll have discussions. It's going to be fun. The most important thing is that it's clear for everybody. So just ask questions. So that's the evaluate function in one slide. So now we have our random population. We know how to evaluate each one of them, so we have a clue of which one is better than the other. And now we're going to enter the while loop. We're going to enter the loop that we're in right now, right? Because we're still generating generation after generation after generation. So our termination condition is not satisfied. But what is a termination condition, a possible termination condition? The funny thing to mention here is that EAs are stochastic, as in they're not going to give you the same solution every time, because it's based on probability somewhat, because mutation is based on probability.
If
So
you
you
use
may
mutation.
never find, sorry?
Only if you use mutation.
Only if you use mutation, yeah, that's a good point. You have like several, you have
You can also only use recombination, and then you don't have the.
yeah, you actually have quite a few confusing names for genetic algorithms, evolutionary programming, evolutionary algorithms, and they all have like thoughts about how you should use recombination, mutation, and whatever. But the evolutionary algorithms I'm talking about that use mutation are stochastic, and they may never find an optimum. This is what a normal evolutionary algorithm looks like during its run. So this is the best of the in the population, in the current population, and this is time. So it skyrockets at the beginning and then just like fades out a bit. It's good to know for future reference. So what we usually do with termination condition is a combination of things that are sure to terminate. For example, time. I'm going to run for an hour. I want to run 10,000 generations. And a goal, because we're trying to reach a goal using evolutionary algorithms. We're trying to reach a fitness threshold. For example, the antenna with NASA. We need it to function according to the spec, at least. So that's a fitness threshold. If it works in the model using the antenna, then we're good. Doesn't have to work better than that, it just has to work. Right? With a charting salesman problem, I have to be home for supper by 6. Then I don't need to be home at 5:30, I need to be home at 6. So that's an example. So that will be a fitness threshold. The funny thing to mention is that, here we get into the same graph again. You can also check for a fitness improvement stagnation. So if you are seeing that you're in this area, then it might be time to stop, because you're not going to progress any further that much, or at least it's going to take a lot of time, and you might not want that. So you can choose a termination condition, and while we're in this loop, the first thing we're going to do is to select parents to reproduce. And how do we do that? Well, where x is the number of parents, we can just pick x best. We have a population of, say, 100. We want to pick the 10 best of the population of 100. We can also pick random. And we can also pick best x out of random y, or random this, and then, or the best and then a random out of that. There are several possibilities. Why would it be a good idea to use a form of randomness in selecting parents?
Yeah,
you already have some.
Sorry, yeah.
I'm thinking here.
Sorry.
Go ahead. No, it's fine.
Well, to prevent overfitting to the environment, you want to have some diversity.
Yeah, that's true. Another way to put that would be to say that you have, so for example, you have the solution sphere, if you call it that, the solution space, and it could be like this. Like small hill, large hill, the one you want to be at, and a few small ones. Suppose you have a population that goes for the best, and they are all here in this region, and then you're going to climb the hill, stay at the top because it doesn't have anyone around it, so you can't get to the large hill anymore. It's called like getting stuck in a local optimum.
Yeah.
Which is also one of the reasons I'm fond of mutation as opposed to other people probably. Because mutation helps you hop to other hills you want to climb. I hope it gets clearer as we go. So in our example, we're going to use best x out of random y. It's just a choice. Depends on the problem as well. It's a bit too much to go into that right now. So, some Java code again. Well, this is our parent selection. And what we do first is we're just going to initialize the temp population and some random candidates. I'm going to show you a bit why we need the temp population. And why we want to create the first parent pool where we're going to randomize from, right? Or where we're going to pick our best from. So the parent pool size is something we can tweak. So we can say, okay, I want to pick the 20 random and 10 best. Then the parent pool size will be 20. We're just going to say, okay, give me a randomly selected index from the population, get the solution, and add it to the random candidates. So that's the random candidates we're picking. This is the reason we need a temp population, because we have to remove it from the temp population, because otherwise we would pick it twice. Took me some time to find that bug. And if you try to remove it from the original one, you get a concurrent modification exception. So we don't want that. So we use a temp population. We're not talking about performance here, because otherwise you would probably do it differently. I'm interested in showing you the concept. So this is a neat little thing. And now we have our random candidates, say 20, and we want to pick 10 best. So what we do first is we sort the random candidates, because we implemented a comparable that uses the fitness function. So now the best candidates are up front, and the worst will be at the back. And now we just sublist the random candidates to the size of our parent selection size, and we're good to go. So also the parent selection size, we made it to one slide. So now that we have our prized parents, we would like them to recombine. And the funny thing is, half-half doesn't work in this example. So with us humans, it's really easy. You just pick half the DNA of the mother, half the DNA of the father, you smash it together, and 9 months later, voila, there we are. Why wouldn't that work in this particular problem, the traveling salesman problem?
Duplicate cities.
Duplicate cities, thank you. So what we have to do, so duplicate cities, because if you take half of one, half of the other, and we have to visit every city only once, you might get the same city twice. And we want to prevent that. So we're going to use something that's called cut and cross fill. And I'm just going to show you, because that makes it a lot easier. So what we're going to do is we have 2 parents, and we're going to create 2 children, 2 offspring. And I'm going to start with 1 to make the process a bit easier. And what we do is we randomly select a cutoff index, which in this case would be over here. And we copy the left side of that in the child.
Yeah.
So that would be the cut part. Now we're going to do the cross-fill part. And the cross-fill part checks for this empty space from the index on over here. So the index here was, say, 2, like 0, 1, 2. Then we start here. 5, we don't have 5 yet. So let's add that one. We have 4 already, because it's over here. We have 2 already as well. And now we get back to here. 3, we don't have that one yet. 6, we don't have that one either. And the advantage of doing it like this is that you get to keep the ordering of both parents, in a way. We can do half-half, unfortunately, but we can try to keep some of the ordering in place of both parents. Now here it doesn't seem like that, maybe because it's really small, but suppose you have 100 cities, then you keep a lot of the ordering of both parents in the child. And the other child is going to do the same, but then the other way around. So we're going to cut off here, look for these in the other parent. Is that clear to everybody? Yeah. Otherwise, give a shout out and we'll discuss it. So, what does it look like in code? Well, we have 2 parent routes we want, so we get the routes from both parents. We initialize the city routes, which are empty now. We randomize the cut index. And we copy the first part of the parents cut into the children. So for route 1, we add all from parent route 1, we sublist 0 to the cut index, and for route 2, we do the same with parent route 2. Just as I showed you on the slide before. Now we're going to do the cross-fill part. We're going to do that in another method. So this is the only thing we can do in one slide. And then we're going to create the new children by just creating new candidate solutions with those routes. And then we're doing something with listing and stuff, but I'm omitting that for layout reasons. It doesn't do anything important. So what does this cross-fill look like? So we already did the cut index part. Now we're doing the cross-fill part. So we just need a for loop that goes from the cut index to the end, checks the route, the next city on the route, check if the new child already contains the route, and if not, add it. And we also need to have a for loop from the beginning to the cut index, and that's it. That's our cross-fill. So mutation. Anyone, any idea of how we would implement mutation?
I know, so to say.
Change randomly.
Change randomly. What do we change randomly?
Switch.
Switch. Yes, thank you. Why can't we change one city randomly?
Why weren't we doing it?
Well, because then we get duplicate cities.
Oh,
So yeah. So we switch. So we're gonna swap. Swap to the rescue. We're just gonna pick. Bless you. Just gonna pick 2 cities. Switch them around, and that's our mutation. So what does it look like in code? Well, we initialize random. We get a random index for a first city, index of a second city. This is one of those bugs. Again, that takes you a while. Make sure that the index of the first city isn't the index of the second city because we're doing random. I was having mutations that weren't doing anything, so yay for unit test. And then we just get them from the route and switch them. Changer. That's it basically. Really simple. I mean, recombination was pretty simple, mutation was pretty simple, parent selection, pretty simple methods, but really powerful concepts. And if it works, you have to let the algorithm work for you, and then like magical things happen. But we'll see that in the demo, hopefully. The demo gods are with me. We already know how to evaluate. Well, we have some new candidates, so we have to evaluate them as well. And then we select the new individuals for the next generation, and then the whole party starts from the beginning again. So how do we select? It's also called the replacement strategy, or you can use a replacement strategy, for example, where you replace the new children with the former parents. You can do nothing. You can just let the population grow. Or you can replace the worst, for example, or you can throw away the half, or whatever. There are a lot of ways to do evolutionary algorithms, just showing you some of the things that you can do that make sense. And we're just going to use replace worst. We're going to select survivors by sorting the population. We have this compare implemented. So the best individuals are up front, the worst are at the back. And what we do now is we just sub this to the population size we would like. And you see all these like fields, if you were. These are all tweakable. And in the interface I'm going to show you in a bit, you can actually tweak these settings. So you can check out what works for your problem. So what did we do? Just a quick recap. We initialized the population with random candidate solutions. We evaluated each candidate. We started a while loop with hopefully a good termination condition. We selected the parents, recombined them, mutated some of them, evaluated the new candidates, and selected individuals for the next generation. And that's it. That's our evolutionary algorithm. And this is actually the evolutionary algorithm implemented. The code I just showed you, and of course this pseudocode implemented, is the code I used for this demo. So that's pretty simple for something so powerful, but I'm going to show you that in a second.
I might have missed it. What was the termination condition?
Okay, so there are...
What termination condition did you use?
Okay, I'm going to show you in the interface that you can actually select a couple of things.
Okay.
But you can say, for example, for the Salesman Problem, I would like the route to be under 2,000 miles.
Okay.
But I would also like it to end when I press the stop button and when I when it has run for, say, 30,000 generations, because I don't want to wait for it for a week, which is possible, because it will just keep on going. So tuning, I already talked about it a bit, but you can tune mutation probability, the population size you're using, the number of offspring, termination condition, number of runs or fitness or whatever. Parent selection, survival selection, initialization is done randomly now. There are some that say maybe you should implement some heuristics to bump the evolutionary algorithm to a new level before even starting the evolutionary algorithm. But because we already talked about the normal course of an evolutionary algorithm, why put effort into bumping it up if it's going to bump it up anyway in the first few seconds or units, or because you're not going to use a heuristic to get it there, because why are you using evolutionary algorithms then? And yeah, this doesn't add much value, but it depends on the problem. So it's demo time. The backend has the Java code I just showed, nothing more. I used NASA Worldwind to do the calculations, as in what is the distance between Amsterdam and Madrid. I get a number back. That's the only thing I didn't implement. On the front end, I use some Angular that you don't want to see, and if you do, you have to take a shower if you get home, because it's that bad. With some bootstrapping to make it look nice, and Google Maps to plot it on the map. So if it works, you can also find it on GitHub. I'll see your pull requests. The first is yet to come. No, that's actually not true. Oh, that's actually not true because, okay, this is going to be fun. So I talked about JCore, as in that we started this year. And we have this guy called Dennis. And do you guys know Josh Long? From the Spring Advocate, right? Spring Developer Advocate. And he was showing us that you can actually do a custom banner.
Oh, yes.
If somebody knows already. You can do a custom banner in when you start up your Spring Boot application. So this guy. So let's take a moment to appreciate this awesome artwork by Dennis. Oh man, this is. I mean, this is beautiful. Okay, so this uses Spring Boot. Oh, there we go. So we have backend, Spring Boot, we run it. This is an Angular app, so I'm just going to use a simple HTTP server. This is an alias for a Python simple HTTP server running on 8001. And creates the demo gods. If I refresh, it works. Hallelujah. And the first thing I want to show you before we head into what we're actually doing here is these are the things we can fidget the dials with. This is the nutty professor kind of stuff, where I'm just going to try out or theorize about what will be the best set of settings to tackle this problem with. And this we already talked about. This is fun to mention because Ray Chang is developer advocate for Google Cloud Platform. I talked to him at JFall, and we're just talking and having a beer and having fun. And when we talked about evolutionary algorithms, and he said, right straight from the bat, like, we should do this distributively, and we had a lot of fun, like, thinking about how we would do that. And we actually spent an evening during JFocus implementing it in parallel as well, so we could actually deploy it on the cloud. So that's pretty cool. Not going to talk about this, but I'll talk about the rest as well. Just thought it was funny to mention. We submitted a talk for DevOps, so let's hope it's accepted. I know I said I wasn't going to do this presentation again, but that's a slightly different presentation. So, so what we're seeing here is almost all of the capitals of Europe, and we want to solve this traveling salesman problem. So seeing the amount of numbers of cities, I think it's about 23 cities. Brute force would take a really long time to do this. So I'm going to start off with the really high setting, which, as you might have seen, changed a bit of these settings to wow you, and then I'll explain like different possible settings. So if we play this, you can see the fitness here, which you want to minimize. Right, so we want this as low as possible, and this is the number of generations that we have. And this is actually pretty cool seeing, so it's showing the best solution of the current population. And this is actually the best solution there is. And the beautiful thing to note is that this actually looks like an algorithm, an evolutionary algorithm, but upside down, because we're minimizing instead of maximizing.
Mm-hmm.
So this is just the code I showed you in a few slides, and it implements an evolutionary algorithm. How cool is that? Nice. Nice. I was just gonna wait till that happens. So.
Question, can you also buy a flight now?
He also buy a flight, yeah. I should monetize this. Yeah.
You must sell it to KLM or something.
Exactly. Well, there are a lot of people
This
who
was the best solution?
Sorry?
You said this was the best solution?
Yep.
How do you know?
In distance.
It's because of the distance, it's because I checked sometimes. I still have on my list to do a brute force implementation,
Right.
but I didn't because I'm a lazy developer.
So why is London in there?
Oh, damn, that's actually a good
Because it's
question.
still a European capital.
Yeah, it's currently still European capital.
It
Well,
will
it
stay
remains a European
yeah.
capital.
There's a difference between the EU and Europe.
Why is Luxembourg missing?
Most of the capitals. Amsterdam is missing as well, I think.
No.
Oh, that's true. Yeah. Cool. Okay, so we have several settings. We can medium, high, low. That's just something I entered like this. These are presets. And as you can see, this is this gets stuck in a local optimum. So the thing we talked about, like getting up a slightly smaller hill than the one we're actually looking for. And it just gets stuck and doesn't get any further. I think it's the same here. It's probably not. So any idea why these starting points are different?
Random?
Yeah. So we're initializing a random population. So I'm asking these questions to both stay awake and to try to make you think about what is actually happening. So we're still randomly initializing a population, and then trying to get the best out of it to get the best route. So I'm just going to show you this one more time because now you see what's actually happening, so you can bask in the beauty of the algorithm actually trying to find generation upon generation the best solution. And you can see here as well that again the graph is behaving as an evolutionary algorithm. And this again has the supposed best solution.
Did you also try to start with the best solution and then work further on to see if it's improving?
Okay, check. No, I haven't, but I'm fairly sure that it wouldn't do anything because you're already at the best solution.
But you're thinking that's the best solution. It could be even better.
I'm pretty so I'm doing this for a while. I'm pretty sure that it's not going to get any further than this. I let it run for a night one time and didn't get any further than this.
It shouldn't do any different, right? Starting from this point rather than starting with a random, because once you're at this point, it will always use this as the top result
Yeah.
with this strategy.
Yeah. So you're saying it is different, or
No, it would never
no,
be
exactly.
different.
So yeah,
There's
that's
no point
actually
in
what I'm
testing.
saying. Yeah.
And your demo doesn't
No.
look that cool because now it just tracks all these lines and
Yeah. So funny story is that I was showing this demo, and somebody came up to me after the presentation and said, "What were you demoing?" And I was like, "Dude, you saw the super cool. You saw the route like changing and getting to the best solution." He was like, "No, show me again." So these lines were red, and he was colorblind, so. So that was a funny story.
Everybody's like, ooh.
So I hope I've proven a bit that the algorithm actually works and it's pretty simple to implement. And I just automatically
Evolution.
evolution. So I have this habit of when I'm standing up from my laptop, I close it.
Okay.
No, now I so I use these implementations of these methods in plain Java code to have a nice way of showing you how evolutionary algorithms work. but there are some pretty great Java frameworks out there that do a lot of work for you. There's the Watchmaker framework. Yeah, go there. It's really fun. They have a lot of demos on the website as well. You can fidget with the dials as well. You can just see what it can do for you, and you can use the library to create evolutionary algorithms of your own. There's also JGAP. The left one is more like open source, hip open source, and the right one is more like academic open source, so it's a bit more dusty, or how do you say that in English? It's a bit more academic, I believe is another word for the word would be. It's pretty good, but this has like a nicer UI interface and everything, so this would be a nice one to start. I'm waiting for someone to take the picture. I'm going to upload the slides as well, by the way, or make the doors upload the slides. And there are several others, but the first two I would recommend. So with great power comes great responsibility. This is going to be the checklist to see if you should use it, because otherwise you're probably going to, you may be wasting your time. So the first question to ask yourself is, am I sure I cannot find a solution using a brute force approach? Because evolutionary algorithm design does take time, and brute force might not. So, and the real question would be, would it terminate within a reasonable amount of time? So if the answer is yes, you're sure you cannot find a brute force approach, am I facing this optimization or search problem? Because that's the problem we're trying to solve. That's the problem that evolutionary algorithms solve. Can I encode a candidate solution to the problem? Is the representation possible? Can we see what a route is to be able to think about mutation, recombination, evaluation? Because if you can't represent it, you can't think or reason with it. Can I determine the fitness of a candidate solution? If you can't compare one individual with another, what are you doing? I mean, then you have a population of individuals. Yay. And if all answers are yes, just do it. Worst case, you're going to have a lot of fun. So one does not simply end a presentation without answering questions. Do you have any questions? Luckily, you already asked them during the presentation, whichever you like.
Well, I don't have questions, but I have some remarks.
Yep.
I really recommend to read the book about evolutionary computing of Gusti Ivan.
Oh yeah.
It's really a good book because it gives an introduction about all approaches of evolutionary computing and what's the difference between each pros and the cons. Yep. And there are also some nice evolutionary algorithms stuff that's already implemented. So they're using for music and also for playing Mario games. So it's pretty cool to use it.
Yeah.
So I strongly recommend to play with it.
Yeah. Actually, so the funny thing is, a question for you. Did you go to the Free University?